Human language is qualitative and abstract. To process text at scale, natural language processing requires a mechanism to translate that meaning into quantitative mathematics. The theoretical basis for this translation is the distributional hypothesis. Established by linguist J.R. Firth in 1957, the hypothesis states that words occurring in similar contexts share similar meanings. The skipgram architecture puts this theory into practice. It takes a single target word and attempts to predict its neighboring context within a specific sliding window. The concept is elegant. However, attempting to optimize this prediction using standard neural network mathematics creates a severe computational roadblock. Typically, when a network needs to calculate a probability distribution across multiple classes, it uses the softmax function. The numerator of the softmax equation makes sense for this task. It takes the exponentiated dot product of the target word vector and a specific context word vector. The more similar the vectors, the higher the resulting value. This is the formal softmax equation. The denominator here, the normalizing constant, is the source of structural failure. To output a valid probability, the network must calculate the dot product between the target word and every single word in the vocabulary for every single update. In 2013, a research team led by Tomas Mikolov bypassed this bottleneck using an intervention called negative sampling. While often described as a computational speed hack, negative sampling mathematically rewrites the learning objective from the ground up. Bypassing the softmax bottleneck requires abandoning the attempt to predict a specific context word out of the entire dictionary. Instead, the model performs binary logistic regression. Rather than outputting a distribution over millions of words, the model is only asked to output a single probability between 0 and 1. We start by defining a true condition. We extract a target word and its context neighbor from the text, labeling this pair D equals 1. Next, the false condition. We pair that same target word with a randomly drawn dictionary word, labeling it noise, or D equals 0. Now, the neural network's job is simplified. Instead of scanning millions of words to find the right neighbor, it acts as a discriminator. It evaluates a single pair of words and asks, is this real text or is it random noise? The overarching goal is to find the parameters that maximize the joint probability of two outcomes, correctly identifying all true pairs and correctly rejecting all noise pairs. We multiply the true distribution by the noise distribution. To prevent computer underflow, taking the logarithm converts these unstable products into manageable sums. Finally, substituting the probability variable with the sigmoid function bounds the vectors between 0 and 1, yielding the final negative sampling objective function. The left half of this equation optimizes for the real text. It drives up the dot product of the true word and its context, moving their vectors closer together. The right half optimizes for the synthetic data. It drives down the dot product of the word and the randomly drawn noise samples, pushing their vectors apart. By drawing a few negative samples, the model optimizes the vectors without ever calculating the massive softmax denominator. Applying this to a massive corpus of text requires specific data engineering. The math only holds up if the noise pairs are drawn from a meticulously engineered distribution. If the algorithm uses purely uniform sampling, the model will be overwhelmed by high-frequency stopwords. Comparing a target word against the, is, or a thousands of times provides no meaningful semantic contrast. This chart shows a Zipfian distribution, a statistical reality of language where a small number of words dominate the total frequency counts. Mikolov solved this by raising the unigram distribution of the corpus to the 3/4 power in the sampling table. This scaling artificially boosts the sampling rate of rare words. It forces the network to learn fine semantic boundaries rather than simply rejecting common pronouns. This is an area where skipgram outpaces the continuous bag of words architecture. CBOW averages context vectors together, which trains faster but loses the granular resolution required to accurately map rare words. Ultimately, the mathematical theory of Word2Vec is completely dependent on these specific data engineering heuristics to function in reality. Word2Vec and negative sampling successfully established effective embeddings for natural language processing, but the architecture has a limit, polysemy, or the one-word, one-meaning constraint. Take the word bank. In text, it can mean a financial institution, or it can mean the edge of a river. This 2D coordinate graph demonstrates the problem. Word2Vec forces a one-to-one mapping. The word bank is plotted as a single point, stranded halfway between the cluster for finance and the cluster for a river. Because this vector is a fixed coordinate pre-calculated during training, it cannot adapt to new context during inference. Restricting words to a single fixed coordinate was a necessary mathematical compromise, but it prevented models from capturing the inherent variability of natural language. Solving polysemy required contextual embeddings. Powered by bidirectional LSTMs in Elmo and transformer self-attention in BERT, the architecture shifted. Modern architectures calculate word representations as a dynamic function of their surroundings. In these models, a word's vector is dynamically calculated at inference time based on the bidirectional weights of the entire surrounding sequence. This mapping shows what happens when we process the sentence, "I sat by the riverbank." The vector for bank actively shifts its geometry. It is pulled directly into the river cluster based on the contextual presence of the words river and sat. Word2Vec's derivation of negative sampling taught machines the foundational geometry of meaning, but it took the leap to self-attention to finally teach them the fluid, adaptable nature of human thought.